This is the heating curve for water. And a heating curve, basically what I do is I take a sample of something and then I add energy to it at a constant rate. So I'm going to begin with a sample of ice. I'm going to add energy to it at a constant rate. This ice, as energy is being added to it, the temperature of that ice will increase until I get to the melting point. At the melting point, all of the energy that I'm adding into this water sample is going to go towards breaking the lattice structure of the ice, so the temperature is actually not going to increase even though I'm adding energy to it. That is because it takes energy to break apart its solid structure, and this amount of energy is called the delta H fusion, and it has two other names for it. It's called the heat of fusion or the enthalpy of fusion. And at this point both ice and water exist. And the delta H fusion is similar to delta H vap, where instead of the delta H vap is the energy required to vaporize or convert 1 mole of liquid to gas. This is the amount of energy required to convert 1 mole of solid to liquid. And while this phase is going on, the temperature of the sample is not increasing. Once all of my ice has been converted to liquid, then the liquid's temperature will increase until I get to delta H vap. Enthalpy of vaporization, heat of vaporization is the same thing. And the same thing will happen. All of the energy that's added to the sample at this point will not cause the temperature to increase, because that energy is being used to convert the liquid into a gas. And then once I have the gas, then the temperature starts increasing again. So here 2 phase changes have occurred. A phase change from a solid to a liquid and from a liquid to a gas. And most of the time people think the most important part of phase changes, or the determining factor of phase changes, is the temperature. And the temperature is very important, but what the determining factor is going to be is actually quite surprising. It's the vapor pressure. And the reason that temperature is such a big determining factor is because the temperature has a large effect on the vapor pressure. So this should explain why the vapor pressure is the determining factor in a phase change. On the left I have ice, on the right I have water. This is a closed system. Nothing can get in or out. So let me look at, let me first say that solids in fact have a vapor pressure. Liquids obviously have a vapor pressure, and gases have a vapor pressure as well. All of them have a vapor pressure. And what will cause a phase change is when the solid has a greater vapor pressure or the liquid has a greater vapor pressure. It just depends on which one. So let me just go through the examples and show how the vapor pressure is influencing a phase change. On the left is ice, the right is water. Suppose that in the first example, the vapor pressure of the solid is greater than the vapor pressure of the liquid. If the vapor pressure is greater in the solid, then what the solid is going to try to do is give off molecules in order to make the vapor pressure in this chamber equal to its vapor pressure. That's why water evaporates, or any liquid evaporates, when I put it in a closed container. And what that liquid is going to try to do is make the vapor pressure in the air equal to its vapor pressure that it wants. If the liquid in the same chamber has a smaller vapor pressure, then what's going to happen is that this ice is going to try to release molecules in order to make the vapor pressures come to an equilibrium with the solid. But at the same time, the liquid, which has a lesser vapor pressure, it wants to lower the vapor pressure. So what it's going to do is attract molecules into itself. So over time what will happen is all of this solid will disappear and it will end up in the right hand side. If the situation is the opposite, where the vapor pressure of the liquid is greater than the vapor pressure of the solid, then the exact same thing but going the opposite way will occur. The liquid will try to release molecules so that the vapor pressure in the air will be equal to its vapor pressure. At the same time, this solid, with a lesser vapor pressure, it's going to want to reduce the vapor pressure of the air around it. So it's going to take in molecules, and these will become solid. So eventually all of these will go up and end up on this side and be turned into a solid. In the case where the vapor pressure of the solid is equal to the vapor pressure of the liquid, then it will just remain the same. And this is what would be defined as the melting point. When the vapor pressure of the solid is equal to the vapor pressure of the liquid. That's right here. When it's in the solid phase, that is when the vapor pressure of the liquid is greater than the vapor pressure of the solid. When I have water, the vapor pressure of the solid is greater than the vapor pressure of the liquid. See, what's happening is, as the temperature changes, the vapor pressures of the different states, the solid and the liquid, change as well. And eventually, when the temperature is lower, the vapor pressure of the liquid is greater than the vapor pressure of the solid. So imagine if I had a graph, and this is temperature. This might be the say this is the vapor pressure of, we'll say this is the liquid. Actually, I'll say this is ice. And this will be water. So each one of these vapor pressures for the ice and the water will change differently according to temperature. And this will be the melting point. So the temperatures where the vapor pressure of the liquid is greater than the vapor pressure of the solid, then it's going to have a solid form at that particular temperature. But then as the temperature starts increasing, there's going to be a point where they're equal, the vapor pressure of ice and water. And that's going to be defined as a melting point. And then beyond that, the vapor pressure of ice is greater than the vapor pressure of water. So at those temperatures, it's going to form water instead of ice. That's what the temperature has to do with phase changes. It's not entirely dependent on the temperature whether something is a solid, liquid, or a gas. And that brings me to the last part of this, which is a phase change diagram. As the pressure increases, it's going to cause my substance sometimes to be a gas or a liquid. So imagine this is temperature. At low temperatures, it's more likely to be a solid. That makes sense most of the time. Sometimes there will be cases where there will be some weird stuff. Like water is a little bit weird. As the pressure increases, water actually is more favorable in the liquid phase. But let's just forget about that now, for now, and just look at more normal stuff. At low temperatures, things generally want to be a solid. As the temperature increases, then it will more likely become a gas or a liquid. If the pressure is too low, low pressures, it goes directly from solid to gas. Some examples of things that might go from directly solid to gas are, say, dry ice. It has no liquid phase at atmospheric pressure. For this, if I were to increase the pressure, then it might go from gas to liquid, or from solid to liquid to gas, like here. So as the temperature increases, it becomes a liquid, and then the temperature increases more, it becomes a gas. But the whole point of showing this is that at any temperature, the temperature is not the only determining factor of a phase change. Here at this temperature, something could be a gas, or better even select this one right here. At this temperature, depending on the pressure, it could be a gas, it could be a liquid, or it could even be a solid. It just depends on the pressure. And there are a couple points here that I want to explain, and that is this one right here. This is the triple point. And the triple point is where the vapor pressure of the solid is equal to the vapor pressure of the liquid and equal to the vapor pressure of the gas. So that's where the vapor pressure of all three phases are equal. And at this point, all three phases are present. There's liquid, solid, and gas. And this is the other point. This is called the critical point. At this point, anything to the right of it, if I increase the temperature anything beyond this point, no matter how much pressure there is, it will always be a gas. That's what the critical point is.